Now, there's one thing that we didn't really talk about here, which is the duality. So the reason we didn't really talk about duality here is because for discrete time Fourier transform, there's really not a dual form, okay? Because for discrete time Fourier transform, we convert discrete time signal to a spectrum that is continuous, right? So we convert this xn to a spectrum that's continuous using a summation, but we convert the spectrum to a discrete time signal using an integral form, okay? So this integration and summation doesn't really have a dual form, right? So that's why we didn't really talk about duality in the discrete time Fourier transform, okay? But actually, you observe duality in many other places, right? So we talked about duality in continuous time Fourier transform because you have this similar integral form from time going to frequency and frequency going to time. Now, you also have this duality if you look at, let's say, the discrete time Fourier series representation, right, which is for periodic signals. Okay? So if you recall, when looking at this discrete time Fourier series representation, discrete time is written as this discrete linear combination of these frequency components, right? And you extract the Fourier series coefficient by also taking the summation of the conjugate of these frequency components, okay? So you can see here that both going from xn to ak, going from ak to xn and xn to ak give you very similar forms, right? So you have this dual relationship when you're looking at discrete time Fourier series, okay? So then, you will see this duality in several properties of the discrete time Fourier series. So here are just a few examples, right? So for example, time shift corresponds to a phase shift in frequency. Frequency shift corresponds to a time shift in the time domain, corresponds to a phase shift in the time domain signal, right? Or convolution in time corresponds to multiplication in the Fourier series coefficient, and convolution of Fourier series coefficient corresponds to multiplication in time, okay? So these are due to the dual form of the discrete time Fourier series representation, okay? Now, other than this, you can also find duality between the discrete time Fourier transform, right, and the continuous time Fourier series, okay? Continuous time Fourier series, okay? So this is Fourier transform for aperiodic signals, but this is Fourier series for periodic signals, okay? So because if you look at the discrete time Fourier transform, you have going from the spectrum to the time domain a integral, and the time domain to the spectrum with this summation. And for continuous time Fourier series, you have something the other way around, right? So when going from the Fourier series coefficient, which is basically the frequency domain, you go from this ak to x of t, right, through a summation like this. And you go from the time domain signal to these discrete frequency components using an integral similar to this, okay? So if you compare this and this, there indeed is also a dual relationship. So you can sort of summarize where you see this dual relationship through this table here, okay? So here we have continuous time, discrete time, Fourier series, and Fourier transform, okay? Again, Fourier series corresponds to periodic signals. Fourier transform applies to aperiodic signals, okay? Now we know from the previous chapter that continuous time Fourier transform has a duality, okay? Now we just showed that discrete time Fourier transform does not have a duality because you have from discrete time to a continuous spectrum. Okay, you have a summation here and integral here. So there's not a duality here. But if you look at the Fourier series, right, there indeed is a duality between the time and frequency for the Fourier series. Okay? So continuous time Fourier transform, there's duality. Discrete time Fourier series, there's duality. And there's also duality between continuous time Fourier series and discrete time Fourier transform. Okay? So there are these three dualities that you can explore, to help you derive, similar relationships from one to the other. Okay? All right. So here we have a couple of examples, right? Maybe I just do one of them, and then you can try to do the other. Okay? So they're just basic. You can obtain these results just by a simple change of variable. Okay. So for example, in this 5.16, suppose that you're asked to find the Fourier. You're asked to find the Fourier transform of this the Fourier series of this discrete time periodic signal xn. Okay, that looks something like this. Okay. Now suppose you know that the Fourier series of this periodic signal Gn, right? Suppose this Gn is periodic. So suppose you have this signal Gn, okay, that is basically, sort of like a square signal, right? So you have this 1 from -2, -1, 0, 1, and 2, and 0 and everywhere else. Okay. So for this square signal in time, we know that the Fourier series gives you a bk that takes on this sinc-like function. Okay. Now you're asked to find what is the Fourier series of this periodic signal xn that looks the same as the Fourier series of this signal Gn. Okay? So by duality, right, your intuition tells you that the Fourier series of xn should take on this rectangular shape similar to Gn. Okay? But how do you show that? Okay. So we know that bk is 1/9 summation k from -2 to 2. N from -2 to 2, 1 times e to the minus j k 2 pi over 9 n. Okay? So since bk is the Fourier series of this periodic signal, this means that if you plug this signal into this Fourier series formula, right, you should get bk. Okay? So because of this relationship, you know that this must hold. Okay. Now, we can just do a change of variable where we set k, change k to some n prime, set n to some k prime, and view bk as xk. Okay? So simply by letting k be n prime, n be k prime, and rename Bn prime as xn prime. Okay? So then bk becomes Bn prime, which is xn prime. Okay, I'm just changing a name, nothing changes. So xn prime is equal to 1 over 9, or I can write this 1 over 9 inside. Okay? Oh, anyway, let's do this first. 1 over 9 summation k prime from minus 2 to 2, 1 times e to the minus j n prime 2 pi over 9 k prime. Okay? So I'm only changing n to k prime, k to n prime, right? N to k prime, k to n prime, okay? And I'm just renaming Bn prime as xn prime, okay? So the reason I can do this, I can rename Bn prime as xn prime, is because these two are exactly the same. Okay? So as long as I just change this index k to n, this thing is exactly xn. Okay? Now, next, I want to move this 1 over 9 inside, and then do a change of variable where I replace k prime with minus k. Okay. So here, I want to let k prime be minus k. So then you get summation k from minus 2 to 2, 1 over 9, e to the j, k 2 pi over 9 n prime. Okay? So if you look at this, all right, this is exactly the form of this Fourier series formula. All right. This is exactly, what we have here. Okay? So this means that this coefficient in front of the complex exponential, this thing here in front of the complex exponential should be the Fourier series coefficient of xn. Okay? Hence, the Fourier series coefficient, let's name it ak, is 1 over 9 for k less or equal to 2 and 0 for k greater than 2 and less or equal to 4. And again, this is periodic with period 9. Okay. Okay? Okay. So again, how do we show this? Right, we start out by knowing that this Fourier series representation, this Fourier series relationship holds. Okay. So the fact that this relationship holds tells us that bk, right, this thing here, can be written as this summation. Okay. So this bk here is actually exactly equal to xn if you just change k to n. All right? So if I just change k to n, right, or in fact n prime, okay, I have on the left-hand side this thing, and then on the right-hand side, I get a formula that is equivalent to the Fourier Fourier series representation, and therefore this coefficient in the front is our Fourier series coefficient. Okay. So you can do the same thing for the other example as well. Okay. So for this other example, you start out with this relationship. Okay, so you know that you can write AK. You can write AK as so you can write AK as the integral of the time domain signal over one period. Okay? So you can write AK as the integral of this signal over one period. And then again, just by changing the variables, you'll find that the Fourier transform of this discrete time signal should also take on this rectangular shape in the frequency domain. Okay? So you can show here by duality that x e to the j omega is equal to 1 for omega between minus pi over 2 to pi over 2 and 0 up to pi. Okay? So this is for practice. Okay. And then there's one last thing we want to talk about. Okay. So one last thing we want to talk about is the application to these, systems that can be characterized by linear constant coefficient difference equations. Okay. So we had something similar in continuous time as well, and you can, employ the same treatment to this type of problems in discrete time. Okay. So suppose that you have a linear time invariant system described by this linear constant coefficient difference equation. Okay. So by convolution property, you know that the output spectrum should be equal to the input spectrum times the frequency response. Right. So if you are able to obtain such a relationship, then you will be able to find the frequency response h by simply taking the frequency response, the spectrum of the output, and dividing it by the spectrum of the input. Okay. Now you can do that easily by just taking the Fourier transform of these signals on both sides of the equation. Okay? So when you take the Fourier transform of y of n minus k, then what you have is the spectrum of y with a phase shift depending on k. And similarly for the Fourier transform of x of n minus k. Okay? So by taking the Fourier transform of both sides, we get on the left-hand side summation of ak e to the minus jk omega y e to the j omega k from 0 to capital N. And on the right-hand side, we have summation k from 0 to m bk e to the minus jk omega x e to the j omega. Okay? So then, right, if you divide x to the other side and move this summation of a to the other side, to the right-hand side, you get immediately the frequency response h. Okay? So the frequency response is y over x, which by the above formula is summation bk e to the minus jk omega over summation ak e to the minus jk omega. So this k goes from 0 to n, and this k goes from 0 to m. Okay? So again, this is the same as in the continuous time. Okay. So a couple of examples. Okay. Couple of examples. So in this first example, you have yn minus a, yn minus 1 equal to xn. Okay. So you could, just substitute these coefficients, okay, inside this formula here. Okay, you could just, use this formula and substitute these coefficients inside. Okay, but I would not suggest doing that because, this is actually, quite easy to derive. Okay, so I wouldn't recommend memorizing this formula, but instead, right, to make sure that you're correct, I would do this derivation from the formula directly, okay? Because it doesn't really take you, any time, right? So if you do directly from this formula, from this equation here, take Fourier transform on both sides, you get y e to the j omega minus a e to the minus j omega y e to the j omega. And on the right-hand side, we get x e to the j omega. Okay? So then you get immediately h, which is y over x e to the j omega. And this is 1 over 1 minus a e to the minus j omega. Okay? So it just takes you one more line. Okay? So I wouldn't recommend memorizing this. Okay? Just do the derivation again. It only takes one additional line. Okay? So with a frequency response that looks like this, right? This we're very familiar with. We know that the time domain impulse response will be this decaying exponential a to the power n u n. Okay? So again, see example 5.1 for this inverse transform. Okay. All right, so this second example is similar, right? You could just, do this do this Fourier transform on both sides. So if you do that, you can find the spectrum, the frequency response to be something like this. Right? So this is 2 over 1 minus 3 over 4 e to the minus j omega plus 1 over 8 e to the minus j 2 omega. Okay. Now the key is, what do you do with this, right? We hope to be able to find the inverse Fourier transform to get the impulse response. But how do you do that with this? Okay. So again, we try to relate to what we did in continuous time. So what we could do is that we can write this denominator as the product of two terms. One is 1 minus 1/2 e to the minus j omega, and the other is 1 minus 1 over 4 e to the minus j omega, and 2 in the numerator. Okay. So you can check that this is true, right? 1 times 1 is 1, right? So you have minus 1/2 plus minus 1/4, 1 over 4, which gives you 3 over 4 e to the minus j omega. And then 1/2 times 1 over 4 is 1 over 8. Okay? So the advantage of writing it like this is because then we can use the partial fraction expansion to write this into the summation of two terms. So by partial fraction expansion, right, you get 4 over 1 minus 1/2 e to the minus j omega plus minus 2 over 1 minus 1 over 4 e to the minus j omega. Okay? So once you get something like this, you immediately know what is the time domain response. Right? So the first term gives you 4 times 1/2 to the power n un. And the second term gives you, minus 2, 1 over 4 to the power n un. So for this example, what do we learn? Right? So we know how to obtain the frequency response by taking the Fourier transform on both sides. Right? So that's straightforward. That will give us this. Okay. So the key trick here is to write this, right? Factor the denominator into the product of these two terms, so that you can apply partial fraction expansion to get to write it in terms of the summation of these two terms. And once you get that, because we're familiar with the inverse transform of this type of spectrum, we immediately get the time domain impulse response. Okay, so I would say this is really this step is probably the key to this problem. So we have one last example. This last example is also exactly the same as in continuous time. So I don't know if this is a little bit boring for some of you, right? We went through all these things that are almost exactly the same as continuous time. Okay. So I can do this tomorrow, but basically you just pass a signal of this type through a system with frequency response like this, okay? And then you will have several products of this term that you need to factor out. Okay, so let's do this tomorrow.